Now I want to discuss more details about the mathematical requirement and condition so that a function can be a distance. So I want to introduce this metric space, which we know as a distance. Okay, so in the case of metric space, you can view it as, for example, L2 or L1 distance, where our distance is taking the input as the 2 vector, for example, 1, 2, and maybe 3, comma 5. And then how do we compute the L2 distance? Okay, L2 distance is computed as follows, right? So this is the example of computing the L2 distance. And yeah, it takes these two vectors belonging to the same space and then outputs a single real number. And in order to call this distance as a metric, we have to satisfy the four conditions as follows. So this distance or metric should be always greater than or equal to 0 for any given two vectors, and then this metric or distance should be 0 only when those two vectors are exactly the same. Okay, but there is no other cases that makes this distance or metric to be 0. And then the third condition is this symmetry, when we change or interchange these two vectors, and then we should have the same distance value, right? And then the fourth condition is something called the triangle inequality. So let's see, let me explain this. So for example, in the case of an L2 distance, suppose we are given x and z as 2 points, and then we know the distance between the two is the length of this line segment. And then now we introduce another point y, and then suppose y is located over here, and then we can think of the distance between x and y and z, right? And then the distance, I mean the summation of the two distances between x and y and z will be always greater than or equal to the original distance between x and z. Okay, so that way it is called the triangle inequality. And yeah, when do we satisfy this equality in this triangle inequality? This is when we have y, yeah, lying in the line segment between x and z. Okay, in that case, yeah, we will satisfy this inequality. I mean, yeah, we will satisfy this equality. Okay, so in the case of an L2 or L1 distance, they are all satisfying these four conditions. But what about this KL divergence? Is this really the metric that satisfies these four conditions? It is actually not. So among those four conditions, KL divergence satisfies this guy. Although we haven't proved it, but this KL divergence defined in this manner will always be greater than or equal to 0, and that will become 0 only when P and Q are exactly the same probability distribution. And yeah, so that way the first and the second condition will be satisfied, and the third condition is not satisfied. So this is not a symmetric measure, because if we change P and Q, and then yeah, in these two places it will become Q, and this guy will become P. So the definition will become different, and thus, yeah, carrier divergence is not a symmetric measure. And in the case of triangle inequality, it will not be satisfied either. Yeah. So yeah, we will not prove this, but you should be able to find the counter example easily. But anyways, so KL divergence is not satisfying all of the four conditions, and thus it will not be a metric. But still, we use this KL divergence as a kind of intuitive measure uh, to quantify the difference between the two distribution, probability distribution vectors.